So this is particle kinetics. We have an incline that makes a 20-degree angle with the horizontal. And a 15-kilogram block. And it's sliding down the incline at the instant shown, so its velocity vector is this way. And we have to calculate the acceleration at a few different coefficients of friction. The first part is doing it without any friction. So for part A, there's no friction. Yeah, that's right. You'll still want to use the rotated coordinate system, but a free body diagram has the weight. 15 times 9.81 is 14.715. And then what other forces are acting? That's right. So that's the normal force. And that's perpendicular to the surface, so that's not parallel to the weight force. We're going to use a coordinate system like this. And there's no friction on this one, so this is it. So let's think about how to represent that weight force, because that's the only one that's not lined up with our coordinate system. The weight force is like this. And this angle is 20 degrees. And so what's the angle from the counterclockwise angle from the x-axis to the vector? 250, yep. And so that normal force as a vector is n times cosine of 250, n times sine of 250, which is negative 0.342 n, negative 0.940 n. Yeah. I'm doing the wrong one. Okay. I said that wrong. This is not the normal force. This is the weight force. So, but also don't think of it as an acceleration. It's the force applied by gravity. Oh, that's what we're trying to find. But what we have here is the force applied by gravity. Yeah. Yeah, I mean, you can just think of it as cosine and sine of 250. Yeah. Can someone multiply that for me? Yep. 1.5. Dang it. Thank you. Is anyone multiplying that? No? Okay. Negative 13. So it's actually. Okay. And it actually is 147.15, so that's negative 138 point what? 28? Okay. 50? Okay. Okay, so that's the weight force. So now Newton's second law. From the free body diagram, we have this weight force, negative 50.33, negative 138.28. And then the normal force is in our y direction, our positive y direction. That always just comes in as 0 positive n because of the way we orient the coordinate system. And then that's equal to the mass times the acceleration vector. What do we know about the acceleration? It's parallel to x, so we'll write it as a0. And if it comes out positive, we have a positive a. If it comes out negative, we have a negative a, but it'll tell us what the sign is. And so this thing here is the acceleration vector. So the acceleration vector, let's just use that first equation. So the x equation says a is equal to negative 50.33 divided by 15. What's that? Negative 3.36 meters per second squared. And so if you want the acceleration vector, that's negative 3.360. That's the weight, yeah. And you have to multiply that by the normal force, or add that to the normal force. This is just. So, we want to just set it up in Newton's second law and just solve for the variables. So when we start dealing with friction, that's when we'll have to calculate the normal force and plug that in to calculate the friction force. Okay, so which way is this accelerating, up or down the ramp? Down the ramp. Which way is the velocity vector? Down. So is it speeding up or slowing down? Okay, so without friction, if this is moving down the ramp, it's speeding up. That makes sense. Gravity's making it speed up down the ramp. As you add more friction, what do you think is going to happen to that acceleration? So when we add the first little bit of friction, it's not going to be enough to make the acceleration switch directions. It's just going to make this smaller. It won't be speeding up as much. And then eventually, when we add enough friction, we're going to go from an acceleration down the ramp to we have enough friction that it starts to slow the block down, and then we'll get an acceleration up the ramp. Okay. Where's the normal force? Well, I only use the x equation. When we're solving for friction, we need to calculate that to plug it into the friction force. Because remember, the friction force is the coefficient times the normal. No, we didn't need that equation at all because we're just trying to find acceleration. The only way you'd need that y equation is if you were asked to find that normal force. Right. Right. So now we'll go to one with friction. I'm not going to do all these, but let's go to a coefficient of friction of 0.5. So part C, now the coefficient of kinetic friction is 0.5. What are the units on the coefficient of friction? Nothing. Yep. Because we have that the force of friction is this coefficient times the normal force. What are the units of force of friction? Newtons. Coefficients of the normal force? Newtons. And so what do you multiply by newtons to get newtons? Nothing. Just a number. Okay, so free body diagram in this case, we have two things that are the same. We have the weight of 147.15. We have the normal force perpendicular to the surface. But now there's one more force. Friction. And which way does it point? It's parallel to the surface, and it's opposite the velocity vector. So in this case, it's like this. And this is kinetic friction, so it's 0.5 N. Let's see. We already know that weight force. That doesn't change because of friction. So this force mg still equal to negative 50.28, was it? No, 50.33. Negative 138.28. So now Newton's second law says negative 50.33, negative 138.28 plus 0n plus this 0.5n is in the positive x direction, and 0y is equal to the mass of 15 times the acceleration that's still parallel to the x-axis. Okay, so without friction, we just use the x equation because all we had was numbers and a. But now with friction in there, we have two variables in the x equation. So we always have to use the y equation to solve for n, and then plug that into the x equation. Okay, so the y equation says n is equal to 138.28. Plug that into the x equation. And you get negative 50.33 plus 0.5 times 138.28 is equal to 15a. So negative 50.33 plus 69.14. Is that right? Is equal to 15a. And so positive 18.18 is equal to 15a. And so what's a in this case? .254 meters per second squared. This is the acceleration vector. And so that acceleration vector is positive 1.2540 meters per second squared. Okay, so is this acceleration up or down the ramp? up the ramp. The velocity is still down the ramp, so this time it's slowing down. Okay, so the difference between no friction and a lot of friction is if there's no friction, gravity is enough to keep this thing speeding up down the ramp. If there's a lot of friction, the friction overcomes what gravity's trying to do and slows it down, and eventually it would come to a stop. By the way, this is the acceleration the whole time that the velocity is down the ramp. So if you knew at one instant what the velocity vector was, if you knew it was moving 5 meters per second down the ramp or something, you could use the constant acceleration equations to calculate how long it would take to stop. And then part D, it asks for what coefficients is the block speeding up or slowing down. How do you calculate that? Exactly. Yep. So the crossover point between speeding up and slowing down is when acceleration is 0. So plug in acceleration as 0. No. Yeah. It matters what order you put those in? Yeah. Okay. Is that how all numbers work? No. Just this one. Okay, that's what I thought. All right. Yeah, so for part D, the crossover from speeding up to slowing down is 0 acceleration. So we can write this all the same way. It's the same free body diagram. Newton's second law says negative 50.33, negative 138.28 plus 0n plus negative 0.5n, no, positive 0.5n, 0 is equal to 15 times the 0 acceleration. So n is equal to, from the y equation, 138.28. Plug that into the x equation, and you get, and this one, we're trying to calculate this coefficient of friction. So plug this normal into the x equation. You have negative 50.33 plus 138.28 mu sub k is equal to 0. And so what do you get from mu sub k? .39. 0.36. Okay, so it had to be in between the two that we tried before. It was basically a coefficient of 0 and a coefficient of 0.5, and we got 0.36. Any questions about any of that? This is like the Omni Theater for you guys over there. We should do this in the Omni Theater. That'd be awesome. Do we have, is there any money left in the budget, Meredith? For renting the Omni Theater 3 days a week?
I am low on the total.
Oh. Okay. Maybe we could have a bake sale. Okay, number 22. Okay, so this time the incline's faced the other way. The angle is 25 degrees. So we have a 10 kilogram box and a 7 kilogram box. And 100 Newton force applied this way. And at this instant, the blocks are sliding down the incline. There's no reason that has to be the case, though, because the velocity vector doesn't depend on, well, it just doesn't. So the direction they're moving depends on the stuff that happened up until this instant. So even if this 100 Newton force was applied this way, and you had gravity trying to pull them down and the 100 Newton force trying to push them down, they could at this instant be moving in that direction because of tons of forces that have been acting in the instant right before this, or for the hour before this, getting it up to a high speed, All right, so coefficient of kinetic friction for each box is 0.15. And we want to calculate the acceleration of the two boxes, and the force vector, the 10 applied to the 10 by the 7. In problems like this, we have to calculate the acceleration first, no matter what. So what are we going to isolate to calculate the acceleration of the two boxes? Both together, yep. So free body diagram of both. So there's a weight straight down of 17 times 9.81. What's that? One 147.15 plus 19.62. 166. And then we have this total normal force. And then we have 100 Newton force. Okay, so there's the coordinate system. Here's the weight. What's the counterclockwise angle in this one from the x-axis to the weight force? Yeah, so you go here, it's 270 to there, and then you go another 25. So theta is equal to 295. And so the weight force is equal to 166.77 times cosine of 295 and 166.77 times the sine of 295. Could someone calculate those two? Yes.
Sine is negative 151.145.
Say it again.
Negative 151.145. That's for sine.
Sine, okay. 151. 78. 70.48. So yeah, as far as using 65 and said yes, if when that stuff makes sense to you, go ahead and do it. That's a good habit to get into. But if you get confused about it, you know you can always do it this way.
Wait, this is part A, right?
Yeah, we're trying to calculate the acceleration.
Okay.
That's why we isolated both of them together. God dang it. There is friction. I didn't put that in. Okay, so 0.15. Okay, this is sliding down the ramp. And so the friction force has to be up the ramp. And its magnitude is 0.15 times that N total. Yep. Doesn't matter when you get it, just that you get it. Okay. Yeah. Someone else have a question? Yeah, that's right. Okay, so the normal for the Newton's second law says 70.48 negative 151.145 plus 0 N total plus negative 100, 0 plus negative 0.15 times N total, 0. There's 4 forces in the free body diagram. We have 4 forces here, so we got everything. And that's equal to the mass of 17, times the acceleration, which is parallel to the x-axis only. Now, yep. So then the y equation says that total normal force is equal to 151.145. Plug that into the x equation, and it says 70.48 minus 100 minus 0.15 times 151.145 is equal to 17A. And could someone calculate A? Negative 3.07 meters per second squared. So the acceleration vector is negative 3.070. Okay, is it accelerating up or down the ramp? It's accelerating up the ramp. The velocity, is it up or down the ramp? Down. And so is this speeding up or slowing down? Slowing down, yep. And you could use constant acceleration equations to calculate how long it would take to stop. And then part B, what's the force vector applied to the 10 kilogram box by the 7 kilogram box? No. So what we're going to draw a totally new free body diagram, go through these calculations again. So free body diagram, what's the easiest one to isolate here, the 10 or the 7? Well, we're looking for the force on the 10, and so we want to isolate the 10. On the 10 by the 7. On the 10 by the 7. Yeah. Question? Yeah? Okay, so we'll isolate the 10 kilogram box. We have a weight acting down of 98.1. We have a normal force that I'll call N10. These are sliding down the incline, so we have a friction force up the incline of 0.15 times N10. Is that all the forces, or is there anything else? The force applied by 7, that's right. So I'll just write this as R, but that's the force vector we're trying to calculate. I got friction. Mm-hmm.
Okay, so the friction is the x-axis, the normal force.
Right.
So the normal force comes in twice.
Right. Yep. That's why. So you always have to do the y equation first to calculate n, and then plug n into the x equation for the friction. Okay, so this is a new weight force, so we need to calculate the components. The magnitude's 98.1. The angle is the same as it was before, 295. And so that weight force is 98.1 times cosine of 295, 98.1 times sine of 295. And what do you get for those? Negative 88.91. Okay, so Newton's second law says 41.46 negative 88.91 plus 0 and 10 plus negative R 0 plus negative 0.15 and 10 0 is equal to the mass 10 times the acceleration that we just calculated, negative 3.070. The y equation says N10 is equal to 88.91. And the x equation says 41.46 minus R minus 0.15 times 88.91 is equal to negative 30.7. And so, can someone calculate R? R is negative. Okay, well, tell me again what it is. 2.58. Okay, so let's see here. No, that's not right. It should come out positive. 58.8. Okay. And I knew it had to come out positive because the way we set it up was, yeah. This is a useful thing to be able to like see in your answers when you're done. So I just want to explain how so we set it up so a positive value of R means that this box here is pushing on this one. If we got a negative value for R here, it would mean that the 7 kilogram block is pulling down the ramp on the 10 kilogram. You could get that answer if that problem was set up wrong. Basically, like if that problem represented something that wouldn't happen physically. But on those kind of problems, if you're representing a pushing force, you should get a positive value out. Any questions about that one? Okay, 23. So this one, the incline is actually a wall. And the block is there, and you're applying a force vector to it of 300 newtons at an angle of 30 degrees above the horizontal. The mass is 2 kilograms. And at this instant, the block is sliding down the wall. Okay, we're going to still use a coordinate system that's, yeah. Newtons is at that instant. What isn't a representation or, isn't defined by what's happening at that instant is the direction of motion. Okay, so this arrow I could have drawn going down, going up, without changing any of these forces, because these forces don't determine the velocity. What determines the velocity is all the forces that happen before this instant.
Oh, so we can't assume that the box is, because it's sliding down but you're pushing up, we can't assume that the box is too heavy for the 300 newtons to push it up. We don't know that.
Well, we don't want to assume anything like that. But I mean, even if you could look at it, even if every force on this was acting down, and you're like, okay, it's definitely accelerating down. There's nothing that would make it accelerate up. You could still have a velocity going this way. And the way that works is like, well, imagine like a train, like when a train runs into a car or something. Think of the forces that are acting. Okay, so yeah, so here's the train, right? This long train. and it's hitting a car. Okay, so there's a force that way from the car. And it's applying the brakes, which are putting a force on that way. And the engine is off, so there's nothing applying a force this way.
But it'll still take like a mile.
Yeah, but its velocity is still like this, because obviously it's accelerating that direction. There aren't any forces that are counteracting that. But the velocity comes from all the forces that had been applied up to that instant. Right. Okay, so we're still using this coordinate system, which feels a little weird in this case. Our x-axis is pointing straight up now, and our y-axis is pointing out. Anybody have any questions about how I chose that coordinate system? It's the system. The system says the y-axis, we're going to point it straight out of the surface, no matter what the surface is. I think in the next homework assignment, there's one where you're sliding something across the ceiling. That means out of the surface is straight down, and your y-axis is going to be straight down. No. Yes. You should not. That's right. Right. Okay, so free body diagram, and we're trying to figure out the acceleration. There's one without friction and two with different amounts of friction. So free body diagram, here's the box. There's a weight force of 19.62. There's a 300 Newton force there. There's a normal force coming out of the surface. And then I'll just skip right to one of the ones with friction. It's sliding down the incline, so the friction force is up the incline. And it has a magnitude of whatever the coefficient of friction is times the normal force. Okay, so in this one, calculating the components of the weight force is pretty easy because it's just pointing in the negative x direction. So mg is just equal to negative 19.620. Everyone see that? But the one that we're going to have to fiddle with a little is that 300 Newton force. Okay, so to figure this out, you always put the tail of the vector at the origin of the coordinate system. And we're going from the positive x-axis to the vector. So theta is equal to positive 30 degrees. And so this force is equal to 300 times the cosine of 30, 300 times the sine of 30. 300 times the sine of 30 is just 150. 300 times the cosine of 30. Yes? Yes. Yes, thank you. Dang it. I'm having a hard day.
So I know that you made the x is coming out of the wall. So why did we switch on x and y as well?
You always put the y-axis coming straight out of the surface. Yeah. So we're just following the rules that we set up to make this as similar, every problem as similar as possible. Okay, so yes, that was exactly right. Who said that, Alex? You're right. this is the x-axis. So we do have to go all the way around here. This angle is 30 degrees. We got 270 plus 30, so 300 degrees. It'll change the components, but then you could re-express them in the old coordinate system if you wanted. But yeah, the answers we get are only relevant in the coordinate system we use. You just always get to choose, and this is the easiest one to do. Okay, so 300 times cosine of 300 degrees. 300 times sine of 300 degrees. Can someone calculate those? 150. 259.8. Okay, so now we can do Newton's second law. Add up all these forces. So we have 150, negative 259.8. Mm-hmm. No, if you calculate that angle by going counterclockwise from your x-axis, then you just always do cosine and sine.
Oh, but if we always go counterclockwise from this axis,
then you have to change stuff around.
You can just put sine and cosine.
You have to do it sort of case by case, but yeah, you can do it that way. You can, yeah. The easiest way is just to always calculate the full counterclockwise angle from the x-axis. And then it's always cosine and sine. Okay, so we got the 300 Newton force. Now the weight force is negative 19.620. Then the normal force is what it always is, 0n. Even though, you look at it and it's pointing to the left. That's our positive y direction. Then the friction force is in the positive x direction. So 0.5n, 0. One, two, three, 4, and we have 4 here, so we're done. And then the mass, that's equal to the mass, 2 kilograms, times the acceleration. What's the acceleration parallel to in this problem? Yep, what was it parallel to in the other problems? X-axis is always parallel to the x-axis if you rotate your coordinate system this way. So 2 times a0. Yes? Yeah, if you do a different coordinate system and do it right, that's fine with me. But I think this is the way that you'd be happier if you get used to doing it. Okay, so the y equation says n is equal to 259.8. Plug that into the x equation. It says 150 minus 19.62 plus 0.5 times 259.8 is equal to 2a. And so what do you get for a? The normal force is 259.8. So I already did that. Yeah. That one's usually pretty easy. Yeah. I guess I don't know from just looking at it in this case. I don't know because with no friction, is it accelerating up or down? Up. So then this one will either have a smaller acceleration up or an acceleration down. Wait, which way does the friction go? No, so that's not true. I can't say anything about it in this problem.
Oh, so we're doing
Yeah, calculate A.
Yeah, so I got two.
130? 130.14. Yeah. I think this is, you're turning it around starting now, I think. I don't. Okay, so anybody else? I think that looks reasonable. Okay, so the total acceleration vector is equal to 130.140 meters per second squared. Okay, so is it speeding up or slowing down? No, the velocity was down, and this is up, so it's slowing down. And so this is sort of a funny thing that's kind of hard to wrap your head around with this one. With no friction, the acceleration was also positive and was smaller. So this is a case where friction actually made it accelerate more. Okay, so yeah, what does... Friction always tries to slow things down. And so the reason that the acceleration is bigger in this case is because even without friction, the acceleration was slowing it down. Even without friction, it was slowing down. So a bigger acceleration magnitude just means it's slowing down more quickly. And that's what friction does. Right. Yeah. And so that can be sort of confusing, like friction, wait, friction increased the acceleration? Yeah, it increased the acceleration because in this case, the acceleration was making it slow down. Any other questions about that? Okay, let's take a 10-minute break and start at 9. Let's go. Who's ready? Renee? Clara? Okay, so here's what the forces we've talked about so far. 5 force types. You ruined my punchline. No, that's good. You're exactly right. Good job paying attention. Who else would have been able to come up with that? Good. Okay, so here's what we've done so far. Weight, pulling, pushing. Wait, I can't read. Pushing, friction, and now we're on spring forces. Anyone remember? No, we haven't done that yet. We're on spring forces. Anyone remember why I said we're studying spring forces? Because it seems like sort of a random thing to do. I don't think I said anything about rocket ships, really. Yeah. Because a lot of materials behave similarly to springs, and so this is an important one for engineering stuff that you'll do later on, even though it seems sort of funny, like how many things do you deal with that have springs in them, but it's sort of a lead into a lot of engineering applications. Okay, so spring forces. Wait. And the way to think about this is we're calculating the force a spring applies to an attached object. So the first thing we have to do is I have to give you 4 definitions so that I can set up this equation. So first, 4 definitions. The first one is L sub 0. That's the spring's resting length. So L sub 0 is like if you open up a drawer that has springs in it and measure the spring, that's L sub 0 before you apply any forces to it. And then the length of the spring changes if you stretch it or compress it. So this is with no forces applied to it. So that's L sub 0. Now, just regular L is not the resting length, but at some given instant, what's the length of the spring? So I'm going to call that the current resting length, the current length, not resting. The current length of the spring. So if the resting length is 5 centimeters, and then you stretch it a little bit, the current length is like 6.84 centimeters or something. Okay. And then the difference between these is delta L. That's the change in length. So delta L is just equal to L, the current length, minus the resting length. So notice that that has a sign attached to it. If you take the spring out of the drawer and stretch it, is delta L positive or negative? Positive. And if you compress it, positive or negative? Negative, yep. So positive means stretched, and negative means compressed. And then the last definition is this constant K. This is called the stiffness of the spring. So this is something that defines, like, what's the difference between the gigantic springs you use in the struts of a big truck versus the little springs that we have in our drawers in the lab. The difference between those springs is the spring constant. The gigantic ones have a huge spring constant, very hard to deform. The one in that ballpoint pen is a very small spring constant. Okay? The units, or the SI units, are newtons per meter. Newtons per meter are kilogram meters per second squared divided, kilograms per second squared. Yeah, so it makes more sense if you think about it this way. So it's how much force this thing applies when stretched out a certain distance. This is always positive. Big value is a very stiff spring. And a small value is a very flimsy spring. Yeah. Right. Yes. Yeah. Hooke's law. This is Hooke's law. Yeah. So based on these four definitions, this is Hooke's law. The force applied by the spring, remember this is the force applied to an attached object by the spring, is equal to K times delta L, which is equal to K times the quantity L minus L0. You know, you can think about it either of those two ways. And since it's a vector, we need to know the direction. So we're going to assume like the default direction is away from the chosen object, from the attached object. Okay, so this is Hooke's law. And I want you to notice something about this sign convention. If delta L is negative, that's if the spring is compressed. Then the magnitude of F spring is negative. And then the force is toward the attached object. Okay, so the spring going from stretched to compressed changes the direction of the force. And that makes sense if you think about how a spring works. So let's... Okay, so this makes intuitive sense if you think about... So what happens if... So say we have this spring attached to the wall, and it's stretched out. Yeah, that's a big spring. Okay, so in this case, is delta L positive or negative? Positive. And is that spring applying a force toward, so the person is the chosen attached object, is the spring applying a force away from the person or toward the person? Away, yep, because it's a pulling force. And now in this other case, don't forget to draw the sweat things. Okay, in this case, is delta L positive or negative? Negative. It's compressed. And is the spring applying a force toward or away from that person? Toward, because it's pushing on him. It's like punch it, Jim. He's getting ready for the spring sports season. Okay, so let's see how this works in a calculation. So let's say higher. Okay, so let's say we have a spring that has a constant of 150 newtons per meter, and we apply a force of 10 newtons to this attached object with a mass of 2 kilograms. The resting length of the spring is 8 centimeters, so 0.08 meters. And we want to know what's the length of the spring when it's at rest with that force applied. Okay, so free body diagram. There's the object, and now we're going to draw all the forces. There's a weight force of 19.62. There's a normal force up. There's the 10 Newton force here. And now, even though, so is this spring going to be compressed in this setup or stretched in this setup? It's going to be compressed. You know, this force is pushing on it. And so we know that the force is going to be applied towards the object, But we don't have to think about that. That'll come out in the math. We're just always going to assume, and this is what I was saying by that sign convention when I gave Hooke's law. We're always going to assume that that force is away from it. And when the numbers come out and tell us, is it positive or negative, that'll adjust the direction on its own. So I'm just going to write this as this is K times delta L, which I'm going to write as 150 times the quantity L minus 0.08. And I'm going to assume that it's acting away. We know we're going to find out that that assumption was incorrect, but it'll work out on its own. Any questions about the free body diagram? Okay, so Newton's second law says 10, 0 plus 0, negative 19.62 plus 0, n plus, in the positive x direction, 150 times the quantity L minus 0.08, 0, is equal to, we're assuming it's at rest, so the acceleration is 0. And so the x equation says 10 plus 150L minus 12, 1.2. That's 12, right? Minus 12 is equal to 0. And so 150L is equal to 2. And so L is equal to, what's 2 divided by 150? Divided by? 2 divided by 150. 0.013 repeating. Okay, so the original length of the spring was 8 centimeters. After this compression, its length is 1.3 repeating centimeters. So it's compressed. What if we wanted to find out the force that the spring was applying to that object? Yeah, just plug it in. Yep. So plug L in for the L up here, and you get what's 0.013 repeating minus 0.08 times 150. So 150 times 0.013 repeating minus point. Okay. Is equal to negative 10, 0. So notice that in setting up the problem, we assumed that that spring was a pulling force. But once you go through the calculations, it told us, no, it's not acting in the positive direction like we have it drawn. It's acting in the negative x direction with a magnitude of 10. So it's actually pushing on the box, which we know intuitively it has to be. Because it said in the problem, assume it, if it's at rest, what's length? What's the length? Any other questions about that one? Okay, let's do a circular motion one. Okay, so let's say we have this rolling object over here. And it's connected to this center post by a spring. The mass of this object is 0.1 kilograms. And the spring constant is 200 newtons per meter. The spring's resting length is 10 centimeters, so 0.10 meters. And let's say the object's moving this way around the circle. And it moves with a constant angular velocity of positive 5 radians per second. What's the length of the spring? Okay, so free body diagram of the object. Okay, what forces are acting? Gravity, that's into the page, so I'll draw it like this. I'll just write that as mg for now. What else? Normal force. We're assuming there's no friction, but there is a normal force. That's coming out of the page. Anyone have any questions about those directions? And then what other one? There's one more. It'd be weird if there wasn't a spring force in this. Okay, so we're going to assume that that spring force is pulling, and it has a magnitude of 200 times L minus L0. What do we know about the acceleration? This is circular motion. The velocity is this way. Is there any tangential acceleration? No, because it's not. It's a constant angular velocity. So the only thing we have left is centripetal acceleration this way. The magnitude of the centripetal acceleration is omega squared r. How are we going to represent that? Well, we know omega. What is it? 5. Yeah. We don't know r, but we can represent it in terms of a variable that we have already defined. So we have 5 squared. So what are we gonna? How are we gonna represent r? Yep. So we have 5 squared L or 25L. And if we choose a coordinate system like this, The acceleration vector is the same as the centripetal acceleration vector, and it's negative 25L0. Okay. Who's with me? Who thinks they could finish this problem? I like that confidence and that humility. No. I just wanted to know who thought they could do it. Okay, so yeah, exactly. Okay, so let's think about in this coordinate system from above, what forces are acting? Well, in this coordinate system, the weight and the normal don't even show up, so we'll skip those. But we have this spring force. It's in the negative x direction, so negative 200 times the quantity L minus 0.1, and then 0y. That's the only force in that plane, right? And then that's equal to the mass of 0.1 times the acceleration of negative 25L0. And so the x equation says negative 200 times the quantity L minus 0.1 is equal to negative 2.5 L. So negative 200 L plus 20 is equal to negative 2.5 L. And so 20 is equal to 197.5 L. And so what do you get for L? What? No, it's the other way. A little longer than 0.1. 0.101 meters. Not stretched very far, but you can see it's stretched 1 millimeter, I guess. It's a stiff spring and a pretty light thing, not going very fast. But yeah, so that the need to provide centripetal acceleration stretched that spring out. That's what terrible people would describe as the centrifugal force stretched it out. Okay? But what's really happening is that spring is being relied upon to provide centripetal acceleration, and that's what's stretching it out. Any questions? Okay, see you Friday.